The purpose of this video is to describe procedures for graphing parabolas in Vertex form. Just a forewarning before we get started here, this video ended up taking a lot longer than I anticipated ahead of time, so feel free to listen to this in smaller chunks or take notes as you go along the way, because there is a lot of information, though it is helpful in terms of getting through this topic of graphing parabolas. Before we get started on graphing parabolas, let's define what it means to be a quadratic function and look at the different formats we can work with over the next few chapters. A quadratic function is a second-degree equation. It fits under the umbrella of polynomial functions, but in this particular case your highest exponent is 2 on your input variable x. So there are two different formats that you'll see in algebra a lot dealing with quadratic functions. The first one is standard form, f of x equals ax squared plus bx plus c. This you'll see in a lot of application problems and factoring and solving equations type things. Not the best for graphing, even though you'll probably have to do that in some of your courses. In this particular case, again, x is your input, f of x or y is your output. A, b, and c are all coefficients or numbers in the real number system, and a technical side note, a cannot equal 0 because that would take away that quadratic term. The form that we'll focus on in this video is vertex form, which is much easier to graph from, and hopefully it makes more sense on how the function looks physically as a parabola. The equation here is f of x equals a parentheses x minus h quantity squared plus k. In this case, the coefficient a is again any real number other than 0, and the h and the k represent the vertex of your graph, which we will talk about in a few minutes. The graph of a quadratic function is called a parabola, and you can see the most basic example of this to the right on the screen. You'll see that most people would describe this as a U-shape or a cup that would hold water. The bottom of the graph goes through the origin, and there's a symmetric rate of change going in both directions from there along the x-axis. Some people may talk about domain and range at this point in their courses. Other courses may not go over this until a later point, so if you haven't, you can just skip over this point. Domain is a list of all the possible inputs. If you're thinking about squaring numbers, you're allowed to square whatever numbers you want, so you're allowed to input any number you want. So it makes sense why there's no gaps or holes going from left to right on this graph in the horizontal direction. So we say when that happens, the domain is all real numbers. The range is the list of possible outputs, and if you understand squaring something, we know that when we square something, whether it's originally a positive input or a negative input, the output is always greater than or equal to 0, or a positive number in most cases. So that makes sense here for outputs, and you can see that reflected in the graph where we don't have any blue images below the x-axis, so there's no negative y values listed here. So when we talk about the range, the only possible outputs are greater than or equal to 0. A moment ago I mentioned the bottom of that U-shaped graph we call a parabola. That point is very important. We have a name for it. It's called the vertex. It is either the lowest minimum point of the graph or the highest maximum point of the quadratic graph. There are some cases where we will flip the U-shape upside down, and we will go over how that happens later on in this video. To determine the vertex on your coordinate plane, we will begin by identifying the h and the k that we talked about earlier in the equation of vertex form, or simply by looking at the graph. We will learn another method later when we're dealing with standard form, but that won't be covered in this video. In cases where your graph is already provided for you, all you have to do is to look at the bottom of your parabola or U-shape and look for the point of symmetry at the bottom of your graph. In this particular case, it's the point 2, 3, so that would be considered your vertex. Your h is 2 and your k is 3. Another example here, you're looking at the bottom of this U-shape, and we can see that that is located at the point 0, -4. So your vertex is at 0, -4, and your h is 0, your k is -4. It's important to notice that most of the time you will be given the equation and asked to graph the function. So we need to be able to look at the equation itself and identify the vertex as your first step. It's important to note that there is a negative sign in front of the h in your equation. So the sign in the equation for h will be opposite of the sign for your vertex. So let's take a look at a few examples. So we have f of x equals x minus 3 quantity squared plus 5. the h value will be the opposite of what's on the inside of the parentheses, so that will be a positive 3, and the k value will be the exact same sign of what's on the outside of the parentheses, that is a positive 5. So your vertex is 3, 5 for the first example. The second example, x plus 3 quantity squared plus 5. Again, we have the opposite sign of what's on the inside, so that would be a negative 3. Same sign as what's on the outside, a positive 5. So your vertex is negative 3 and 5. And then as you could guess, the bottom example, x plus 3 on the inside, so my h value will be a negative 3. I've got a minus 5 on the outside, so it'll stay the same, negative 5. And my vertex is negative 3, negative 5. The next three equations are actually a little bit more simple, but sometimes the simpler equations are more difficult for the students to work with. So the first example is x squared plus 5. Now you'll notice there's no parentheses around the x. And if you think about it, the number that is being added to x there is actually 0. So the h value in this case is going to be 0. The k value is 5. In the second example, there is a set of parentheses with an x minus 3 in there, but there is nothing on the outside of the parentheses after squaring, so the number that represents nothing is 0. So remember, your value on the inside is the opposite sign for the vertex, so the h value for the vertex would be 3, and since there's nothing on the outside, the k value is 0. So your vertex here is 3, 0. Very similarly, x plus 3 quantity squared, we have a 3 on the inside, so that is your h value, but we have the opposite sign for the vertex, so that would be a negative 3. There's no value after squaring on the outside, so that value would be 0. So your vertex is negative 3, 0. Another vocabulary term you'll see in most algebra textbooks is called the axis of symmetry. If you draw a vertical line that cuts the parabola right through the vertex, you'll see there's a symmetric piece on the left-hand side and a right-hand side. Symmetric meaning there's a mirror image through that line. There is an equation that goes along with this that they'll often ask you for on standardized tests or just a regular old chapter test. Since this is a vertical line, it is x equals, and since it goes to the vertex, it'll be the x value of the vertex. In this particular graph, if you look at the scale, our vertex is 2, 3, so therefore the equation for the axis of symmetry is x equals 2, since the h value of your vertex is 2. Now that we have the basic information down, let's take a look at the characteristics of the graphs as we go forward. The most basic quadratic function is the function y equals x squared, or f of x equals x squared. We often call parent functions the most basic types of each function if you haven't heard that term before. So we've seen this U shape in a previous graph. I've also listed the y table to the left so you can see how the x coordinates go along with the y coordinates. Remember, anytime you square an input, the output is always going to be positive. I also put 0, 0 right in the middle so you can kind of see the symmetry that goes along with the outputs of 1, 4, and 9 in both directions from the origin 0, 0. You'll also notice if I input a pattern on the graph, instead of going up or down in a linear fashion like you've studied in previous topics, as my x values increase or decrease, there is a definite pattern that is nonlinear that we can pay attention to. If you start at the origin 0, 0, to go one x value over, you're also going up 1 in the y direction. Then going over 1 more in the x direction, you're going up 3 in the y direction. Then going over 1 more in the x direction, you're going up 5 in the y direction. So that pattern 1, 3, 5, you should notice that as we increase x by 1 away from the vertex, we are going up by the next odd value. That is a very important pattern that we can use over and over again with all of these graphs, as long as we don't have a coefficient in front of the x squared. Now, as you may have guessed, there are many variations of this parent function graph, so we will take a look at a lot of the different types of transformations and what you can expect when trying to graph these functions on your own. The first thing we'll look at is what's called a vertical shift. So we'll compare our basic graph here in blue, y equals x squared, to the equation for y equals x squared plus 1. Now, if you think about the order of operations, we are squaring our value of x, which you'll see already in blue, but then we are adding 1 afterwards. So all we're doing is taking all of our outputs for our original equation and just simply adding 1. So you'll see those values reflect in the table, just 1 more added to each output, and you'll see your entire graph has been moved up 1 on the y-axis. The shape is not changed at all, it is just simply shifted in the vertical direction up 1. You'll also notice that same pattern that we talked about before, up 1, up 3, up 5, as we go over away from the vertex 1 unit, is still there. So we didn't change the shape of the graph at all, we just simply moved it up 1 unit. If that example made sense, the next one should be no surprise as well. In this example, we are looking at y equals x squared minus 1 compared to your parent function x squared. You can see order of operations wise, again, we are taking our regular pattern, squaring x, and then simply just subtracting 1 from all of your outputs. So instead of 0, 1, 4, and 9, we're looking at 1 less in each of those. And you can see that again reflected in the table of outputs in green, and you can also see the green graph on the coordinate grid as well has been shifted down 1 in all places, and our pattern up 1, up 3, up 5 is still existing. So all we do when we add or subtract outside of your squaring part of the function is we shift our graph up if we have a positive sign, and we shift our graph down if we have a negative sign. Now, moving your graph in the horizontal direction is a little bit more tricky to understand than the vertical direction. You may have to watch this portion of the video a few times just to get everything down pat. The logical understanding, horizontal is moving your graph to the left or right, so our outputs or our y values here in blue for y equals x squared are not going to change. It's just going to be where they occur in terms of which x value corresponds with them that will differ as we move our graph to the left or to the right depending on what units are happening. Now you can see as an example here, we are changing the value of the function on the inside of parentheses before we square. So that would be, if you remember, you're changing your h value of your vertex. So if you remember that just a little bit, my h value of the vertex here is going to be -1, opposite of the sign on the inside, and the k value from the beginning is 0 since there's nothing out there. So you can see that my vertex has been shifted to the left 1, and that would mean that everything else is also going to shift in that direction. For students that get confused here, I like to have them think of +1 on the inside in the x direction is happening 1 step earlier. So 1 step earlier would be to the left if you think of the x-axis as a timeline. Now on the graph that makes sense, and you can see our graph here in green. Our pattern is still exactly the same, up 1 over 1, up 3 over 1, up 5 over 1, and continuing that pattern. And you can see in the table your y values or your outputs are not changing, they're just shifting to a different x value. They're shifting to 1 x value earlier than they used to be if x is considered a timeline. So +1 on the inside of your operator squaring things is going to move your graph to the left. If shifting to the left makes sense, then shifting to the right shouldn't be too difficult. But again, if you're having trouble with this, please watch it more than once so it makes sense. So again, we are going to look at a horizontal shift compared to the graph y equals x squared here in blue, and we are going to see that instead of adding 1 on the inside in this example, we are subtracting 1 with our equation here in red. Now if adding 1 made your graph happen earlier and move it to the left, you can guess that subtracting 1 is making our graph happen later and moving it to the right. If you remember what we talked about with vertices earlier in the video, you can see that the h value of the vertex would be a +1 and your k value would be 0. So your vertex of this new graph in red is going to be at 1, 0. So it makes sense for the rest of the graph to shift in that direction as well compared to your basic graph y equals x squared. So you can see this is what's happening. Again, your pattern is still the same, up 1 over 1, up 3 over 1, up 5 over 1, and so forth. But your graph has shifted to the right, and in the table, if we're looking at it that way, all of my outputs are the same. They are just shifting down 1 to the next x value to the right on the coordinate grid, or the next input value. So subtracting 1 on the inside of your major operator squaring is going to move your graph 1 step later or move it to the right. Again, this is opposite of our intuition, but it makes sense if you really think about it and start plugging in some numbers. Hopefully shifting your graph up, down, left, or right makes sense. We call that a translation. Now the only thing I didn't go over there is you can combine translations together You can go up and left or down and right, some combination of those, but I didn't want to make this video too long. The next thing that we have to go over is the effect of the a in the equation a parentheses x minus h quantity squared plus k. Your graph, in addition to moving, can also be reflected over the different axes. If you want to reflect your graph over the x-axis, you would make your a value less than 1 or a negative. So if a is greater than 1, say 2, 3, 5, 7, and so forth, your graph is going to maintain that regular U shape upward. But if your graph is a negative, let's say -3, -1, -5, your graph is going to flip over the x-axis and look like an upside down U shape going down. If you want to change the shape of your graph by stretching it out or shrinking it, you can affect that by changing the value of a itself. Disregarding the sign positive or negative, if a is greater than 1, your graph is going to have a vertical stretch. If a is less than 1, as a fraction between 0 and 1, you're going to have a vertical shrink. So you can see here, reflections are very easy. If we compare our regular graph y equals x squared, shown here again in blue, and compare it to y equals negative x squared, remind yourself that you have to square items first, your inputs first, before you apply that negative. So even though our squaring values takes everything to a positive or 0, that negative on the outside is like multiplying by -1, so it'll give each value an opposite sign, making everything either 0 or a negative. So you'll see that will change your graph so it looks like the U shape flipped upside down, and you'll see in the table all of your output values now have the opposite sign of what they used to, and reflections are just simply that easy, just reflecting over the x-axis. If you wanted to reflect over the y-axis, you could include a negative on the inside of parentheses before squaring, but you'll notice because of the symmetry of this graph, that won't make any difference. So a lot of times you won't see that listed in any textbooks. Next, we'll look at an example of vertical stretch. You can see here that I'm comparing your original graph, again here in blue, y equals x squared, to y equals 2x squared. So we're taking all of our outputs in blue there, 1, 4, 9, and we are doubling them. So you can see that obviously the outputs on the table are easy. We have 2, 8, and 18. When you take a look at the graph, however, it might not have been as obvious that your graph is actually going to become more narrow, because for each input of x, your output is going to be double what it used to be. So it makes our graph increase in pace much more quickly than we did in our basic y equals x squared. So our graph is more narrow. Now, obviously the table here was very easy to do, so you may want to just stick with that in terms of graphing inputs and outputs so you don't have to worry too much about your graph. But if you remember that pattern, 1, 3, 5, 7 going up, you just have to simply take that pattern and double it to deal with this graph. So instead of up 1 over 1, up 3 over 1, up 5 over 1, this time you're going to go up 2 over 1, up 6 over 1, up 10 over 1. So we took our regular pattern and multiplied it by a factor of 2. And finally, we have vertical shrinks. This time we are taking a look at a function that has a fraction in front of your x squared as a coefficient, so we can see how that impacts your regular function y equals x squared. So what we're doing is we're taking all of our inputs, we are squaring them as we always have, and then we are multiplying that output by 0.5 or 1/2. Now think about it, multiplying by 1/2 is basically the same thing as dividing by 2. So we're taking all of our regular outputs, 1, 4, and 9, and so forth, and we are dividing all of those values by 2. In that same case, we are taking our regular pattern, 1, 3, 5, 7, and so forth, of going up, and we are multiplying that by a factor of 1/2 or dividing those by 2. So you'll see the pattern now changes to half of each of those numbers, and going up, we are going up at a much slower pace, and that makes your graph wider. So we call it vertical shrink, something that widens your graph. So that's it. As you go forward, you'll probably practice each of these different types of graphs individually in terms of different types of transformations, whether it's a translation up, down, left, or right, a reflection over the x-axis or a stretch or shrink. Sometimes they call those dilations. And as you go forward, they will probably start to combine things together in different parts. Just remember to follow your order of operations just like you have since the beginning of algebra, and hopefully everything's fine with some practice. Thank you so much for watching. I know this video ended up being a little bit long. Don't be afraid to go back and rewind and rewatch certain parts if you forget things or didn't remember to write things down. If you want to see more videos on mathematics, algebra in particular, or other topics, feel free to watch my channel. Thanks so much for watching again.